So we have seen now how the data sources are all perfectly fit for purpose or not. Now we go into looking at some examples about TTS, but also like how we dealt with confounding and how you would actually do causal inference. So we go more into evaluation studies and what made it challenging for us. So first topic is going to be negative control outcomes. Many of us are using negative control outcomes. It's fashionable in pharmacoepi to do that. When I was growing up as a pharmacist and good training in the laboratory, we were always using that already, but pharmacoepi now uses that as well. So we're going to look into how we should use negative control outcomes. So that's the first key topic. And I would like to call for Sophie Bots, who is an assistant professor at University Utrecht. And she's going to tell us about negative control outcomes to identify and measure confounding in a self-controlled risk interval study. Thank you, Sophie.
Yeah, thank you for the introduction. That saves me reading out my title slide. So let's get to it. That is not the button. Do you have maybe the... Okay, slide sabotage. This is the button, okay. I also have a disclosure statement mainly saying that this work has been done in light of the EMA project. Let's get to it. I think most of you actually know this already, but this work that I will be presenting was actually informed and started by the myocarditis signal that was picked up, and this is one of the earliest case reports that was published. And we see that this was published in the beginning of May of 21, and that, as we have heard now many times, it was a young male person presenting to the hospital with chest pain 4 days after their second COVID Moderna vaccination. What is myocarditis? I don't think I have to tell you. It is the inflammation here of the myocardium of the heart, and this leads then to inflammation, and therefore the symptoms that these people are experiencing. And it's of course a very distressing symptom, especially if you're relatively young and healthy and you're not expecting any of this to happen. So after this first case report, there have been a lot of case reports. This was a summary done last year, a case of all the case reports that kind of confirmed what we already know. Now it's the mRNA vaccines, second dose, young men, and it occurs within days. The nice thing that they also found is that it resolves very nicely in about like 95% of cases. So it was not a very serious consequences. But in the 5% where it didn't resolve, you could have very serious consequences. And the timing for this, I think, was very interesting because this was seen, as I said, in the beginning of in May 21, and in July we see this EMA communication, which was kind of just a few days after in the Netherlands, we decided to start vaccinating adolescents with the biotech Pfizer vaccine, which was one of the mRNA vaccines that we just flagged to have this problem. So then I presented this also to epidemiologists, and I asked them, well, what do we do? And before we decide what we should do, there may be some other questions we might like to ask about this association, such as things about causality, size of the risk, the absolute risk, and also benefit. For today, I want to focus on this causality part, because there are many threats to causality if you do observational studies. I do think they're still very useful, despite earlier comments that we might not need them. The main one, I think you all know, is confounding. And we have two types of confounding. Here in this example, we have measured confounders, things that we know and that we can adjust for. But we also have unmeasured confounders, which are either things we know but are poorly or not measured in the databases that we have, or they might even be things we don't know affect the relationship between our exposure and outcome of interest. And this leads to uncertainty. And if you look at causality and confounding in the vaccination space, we ask ourselves, are vaccinated and unvaccinated people comparable? And I think a lot of speakers already said they're probably not, especially in the COVID situation, because we had this channeling of vaccines to specific people depending on the time period. So vaccinated and unvaccinated were not comparable. What do? I think a very nice and elegant solution to this is to compare, instead of vaccinated and unvaccinated people, looking at time within the same person, which is the basis of the self-controlled case series or risk interval design that we used. And the nice thing here is that everything that is stable within the period that you're looking at, any confounder, such as a comorbidity, type 1 diabetes, it's the same for that person. So you will kind of get rid of all that time-fixed confounding. Because what you do is you look at the person when they get vaccinated, you define a control window, which is, for us, was a while back, to before the first vaccination, and then you have risk windows after each dose. And you look, does the event that I'm interested in, myocarditis, does it happen in this risk window or in this control window on average more often for all people? So that solves this time-fixed confounding issue. The next step, of course, is that you look now over time, so there might actually be time-varying confounding in your study. And I think most of you will agree that the COVID-19 pandemic was not a very stable period in our lives, so there was a lot of change over time, which could have induced time-varying confounding. One very nice example is this, where I just very quickly looked at COVID cases, and vaccinations, and then you see if I kind of overlay our design of when we look at these time periods in one person, the COVID incidence in those different risk windows is very different. So if we think that COVID-19 is a confounder, which for a lot of the ACs it is, there's actually a lot of time-varying confounding going on here in your study design that you need to take account for. So solutions here, one of them is adjustment for calendar time, which is very standardly done. But the other one, which is the topic of today, is using negative controls. What are negative controls? In the framework that we used for this study, we define negative controls as something that we can use to rule out possible non-causal interpretations of our results. So in the case you want to know what the effect of caffeine is on blood pressure, it might be, if you just give everybody coffee, that the fact that they're drinking something hot already affects their blood pressure. So you're going to find an association, but it's actually non-causal. So to rule that out, you can have negative controls, like decaffeinated coffee, or in the event that you think just drinking something already affects your blood pressure, you can also have water. And this is a negative control, very easy to do in laboratory or these kind of settings. But now you go into epidemiology. How do we define these negative controls? There is a very nice paper by Lifshitz and colleagues that if you want to know more, I recommend you read it. And they say the essential purpose of a negative control is to reproduce a condition. It cannot involve the hypothesized causal mechanism, but it is very likely to involve the same sources of bias present in the original association. So what does that look like? If you look here on this DAG, we have A as our exposure and Y as our outcome of interest. And in this association, there could be confounders. We have measured confounders and potential unmeasured confounders. If we control for all measured confounders, then the only way our exposure of interest could affect a negative control outcome is through this pathway. This is the only open arrow pathway that is left. So that means that if we use this negative control to kind of give a null association, because we do not expect anything to be there, because it does not involve the causal mechanism. However, if we do find an association between A and N, that means that there is this open kind of backdoor pathway that was opened by these unmeasured confounders. So if we find an association, this might point towards the fact that there is unmeasured confounders present that can also have influenced our association of interest between A and Y. Very short background on that. So how did we do it? Back to this, the myocarditis, and we studied myocarditis using several of the partners that contributed to this analysis. I've put their names on the slide. But where I started actually was making an overview of all the adverse events of interest that we had and trying to figure out what is this kind of confounding structure, so all these relevant confounders that we need to think of for each of these outcomes, because that is the basis for selecting the negative control. First, you need to know what the confounding structure is. So this is kind of unfortunate because I put it on the wrong side for this platform. But myocarditis is over here. So you have a cardiovascular, it is a cardiovascular disease. I subdivided everything by infectious and non-infectious kind of basis, because I think infectious diseases have a very different confounding structure than non-infectious diseases. And then I tried to find all the relevant common risk factors that are associated with myopericarditis, and I made a list of them over here. I did this through very extensive Google searching, finding a lot of medical websites, trying to find all the relevant ones, risk factors that came up repeatedly. I did not do a very exhaustive literature search on the risk factors because I thought most of these are common knowledge. So I was not trying to fully describe every unique little risk factor that was out there, also because if I had that, it would be impossible to match it to something else. So these are the commonly identified risk factors. And then the next step was find a negative control outcome that shares these risk factors. I'm just making sure I'm not falling off the platform. That shares these risk factors like infectious agents, autoimmune disorder, the use of medical or illegal medical compounds, but that is not at all associated with COVID-19 vaccines, because that was the causal link that we're trying to avoid. And then you have to really get out of the box, because once you start thinking, okay, myocarditis has something to do with the heart and heart infectious diseases, soon you get, when you start down that road, you're going to find a lot of similar conditions, but that means that they're so similar that they also have an increased risk after COVID vaccination, so that doesn't work. I also talked to some medical experts about this, some doctors, like how do we do this? And then we came up with a selection of negative controls that we thought would fit most of these risk factors, but were not associated to the COVID-19 vaccines. And I think the important one here that I will talk about is otitis externa. And then the last check we did was informed by the OMOP framework, where they did a similar thing to make kind of like a standard list of negative control exposures. And the last thing we did is a literature review. So I did a very quick search of every negative control I found in PubMed to see if there are any reported case studies or other studies reporting an association between the COVID-19 vaccine and the negative control I selected. And if I found anything, then I removed it from the list. So that was that. And then we can run our study. So that was a lot of preparation work. The study that we ran was part of the myocarditis signal evaluation. It was a self-controlled risk interval study where we had, as I showed you before, we had a control window of 60 days before the first vaccination dose and then vaccine-specific risk windows. And we looked at their outcome, both myocarditis and otitis, in these risk and control windows. And the study ran from the start of September 2020 to the end of data availability. Very shortly, just to show you what was in there, the 5 databases, most of them, as you can see, had Pfizer as their predominant vaccine, except for the UK that also had a lot of AstraZeneca in there. And then when you look at the number of events, you will immediately see that myocarditis, which is the first row, is an extremely rare event. Otitis is a bit more, but also not very often reported, which means that in the end, the number of cases that we could include, especially for the myocarditis, was not that many, but still enough, luckily, and that is also one of the strengths of doing these studies with multiple databases. In our main analysis, very shortly, just to say that we confirmed the idea that the risk was elevated after the second dose of Moderna and Pfizer. We also did sex and age stratified analyses, but they're not shown here because it's not the point of this talk. Because the point of this talk was the negative controls, and we were very relieved and happy to see here that there was actually not a very significant association in any of the situations. So not for the first dose, not for the second, and not for the third, which is not what we were expecting, because when you remember back when we were watching at COVID over time, we were expecting actually, if there was a measured confounding, that it would be higher here and even higher here, because these points, these risk windows were further and further away in time for our control window. So we thought if there is time varying confounding by COVID, it probably gets worse over time with subsequent doses. But that's not what we found. So it was very reassuring. Another thing that we did see, which was very interesting, is that if you looked at the effect by the different databases, that in ARS, so the Italian data, we did actually find for the otitis an association that was a bit more extreme than the other databases. And we thought this, we talked with the ARS experts on this, and one of the things we think might have happened is that because ARS is a hospital database, so emergency department visits, people who had their vaccine and then suddenly had an otitis would be more likely to go to the hospital than people who just had an otitis without the vaccine before it, which could actually create this association between otitis and your COVID-19 vaccine in this specific data set. And this was not seen in the GP data sets because people might be less inclined to visit their GP differently depending on whether they were just vaccinated or not. And this ties in, I think, very nicely with the previous talk about fit for purpose and selecting the proper data sets and also then negative controls for your data set. And that's also where I want to end for today. So we think that this unmeasured confounding in the myocarditis signal specifically was unlikely, even for the later risk windows, which is reassuring. So the self-controlled risk interval study was very robust or confounding. We did see a potentially slight upward bias for the first dose, but we're not sure if that is there or if it's chance. Either way, it wouldn't explain away the main conclusions of the myocarditis work. And I think an important point here is this heterogeneity between data sources and thinking about that when you select your negative controls. Thank you, and thank you to all my collaborators.
Thank you very much, Sophie. What time for one question, because we have multiples. Yes, and I saw Xabier. Yeah.
Thank you for this very nice presentation. I've found something that is not very logical, because from a regulatory perspective, if there is a risk, we want to be sure that there is no bias towards the null value. So it would be much more logical to have a positive control actually outcome, because then if you have negative value both for the positive outcome and the outcome of interest, then you may be very suspicious about the results. Then now, if you also have, because what we want to avoid is that if the results are negative, is that you have a bias toward the null value, and this you can only assess it with a positive control, actually.
Good point. I think positive controls are difficult because I think you would have to, I've seen some work on positive controls, but they were all simulated. So, because then you are sure that it is positive control. I think for this work we didn't have that, and that's why we went for the negative control approach. I think that is still very valuable as a sensitivity analysis to explore whether a measured confounding is there or not, because if you then find something unexpected, you have to dive deeper into your data. So I don't think it would add more uncertainty. One other approach is to use multiple negative controls and see across the board if you see something, but I think that's something we get into during the session, like how we use these negative controls.
But just as a regulator, if the results were negative for myocarditis, I would not be assured that this is a valid study, even because your negative control would not tell anything to me.
Okay. I'm not entirely sure if we're talking on the same wavelength, and I think the negative controls should be interpreted separately from the myocarditis, and that the negative control we expect it to be a null result. So if it is a null result, as we saw here, that's reassuring that the myocarditis effect that we found is unbiased. That's how you should interpret it, but I think we'll get into the whole discussion later.
Thank you, Sophie. Yes, hold on. So I think yeah. Thank you very much, and we like to move on to the next speaker, who I don't know who's presenting, whether it's Dani Prieto Alhambra or Katia Verhamme, I guess. Dani? Hi, Dani.
Yeah.
Hi. So Dani Prieto is a professor of pharmaco and device epidemiology at the University of Oxford, and he is also a professor recently appointed at Erasmus University. So the floor is yours, Dani.
Thank you so much, Miriam. I understand that somebody is sharing my slides. Yeah, fantastic. Well, I'll start also by apologizing for not being there in person. I don't have a horrible virus like Katia, but I have 2 children who are growing old and requiring me to be home more often. So if you go for the next slide, please. Very quick disclosure that this is a study funded by the EMA, but not representing the views of the EMA or the committees. Next slide, please. Okay, so this is a study that we did in an association between COVID vaccine and syndrome, and it's registered in EU PASS. There are 2 objectives. There were more in the study, but there are 2 that are relevant for this talk. The first one was to look at the association between vaccine versus no vaccine and the occurrence of thromboembolic events or TTS while controlling for relevant confounding factors. And the second one is looking at the comparative risk of developing TTS-TE during the administration of different COVID vaccines. And of course, I will use the comparison of an mRNA vaccine versus an adenovirus-based vaccine for illustrative purposes, again, while controlling for relevant confounding factors. Next slide, please. So key design features of our study, we used a new user cohort for objective 1 and a new user active comparator cohort, if you like, for objective 2, because we had 2 different vaccines in that case. For the new user cohort, where we compared vaccinated to unvaccinated, we matched on the day of the vaccination, and the unvaccinated were matched on the same date as the matched pair. The data sources we used have been very well exposed by Katia before, so I'm not going to expand on that. But for objective 1, I will just say that for that one, where we needed really to make sure that unvaccinated time or persons meant unvaccinated time of persons, we only looked at databases with complete vaccine exposure. For adjustments, for confounding adjustments, we use large-scale propensity score matching, and then we use negative control outcomes that I will say in the next slides for a couple of things. Next slide, please. So creating negative control outcomes, as it has been said already, there's a number of ways you can do this. It's not really a task, I will say it that way. In this particular case, we used an automatic generation algorithm that basically goes automatically through product labels and previous literature that is published in that paper that I mentioned in there. After that, we did feasibility counting the target analytical data just to make sure that those conditions appear in the data, because otherwise negative control is not useful if it's not apparent in the data you're using. Then we had a manual review by 2 independent clinical epidemiologists based on current clinical knowledge and epidemiological knowledge. And then after that, we ended up with a list of concept-based phenotypes for selected negative control outcomes. In this particular example, we had a total of 493 potential negative control outcomes, which we knew some of them would work in some databases, some others in others. As you will see, most of the times we had 45 to 50 negative control outcomes in our analysis in a given database. Next slide, please. So we had 2 proposed uses of negative control outcomes. The first one was a stop-go study diagnostic. So we said per protocol, we pre-specified that in any of our analysis, if we found that more than 20% of the negative control outcomes remained associated with the exposure of interest after propensity score matching, that analysis would not continue, as we would think that we had failed to sufficiently reduce or account for confounding by indication. So that was one use of the negative control outcomes. Second use was mitigation against residual confounding. So if there were less than 20% of those negative control outcomes that remained associated with exposure after matching, then we would use empirical calibration to minimize there are, of course, lots of papers on this topic, and you have to imagine that basically what we do is we draw information from the distribution of the negative control, of the association with the negative control outcomes, and we use that to recalibrate the observed estimates. I think this will become more apparent when I show you some results. Next slide, please. Okay, so just to go straight into the findings, I think this is a plot very similar to what Katia was showing earlier, where you have on the x-axis standardized indifferences before matching between two exposed or unexposed groups. In this case, it's objective one, so this is vaccinated versus unvaccinated. On the top panel, you can see for the Pfizer BNT vaccine how before matching, and that's drawn as a vertical line, there's loads of dots, loads of conditions, measurements, and the likes that are different between vaccinated and unvaccinated. Up to propensity score matching, unfortunately, you can still see some evidence of confounding, as denoted by all those little dots that you see above the horizontal line, which is the 0.1 pre-specified threshold. So, and even more so, you see a similar picture for the recipient of Chadell's first dose vaccination. Again, crossing the vertical line of the x-axis and then crossing the horizontal line on the y-axis. Again, with evidence that there is observed residual confounding after propensity score matching. So even with our negative control outcomes, in this case, we would have judged this to be insufficient or suboptimal in terms of adjustment for confounding. Next slide, please. Now, if we use then, we can look at the, of course, at the different dots and see what are the most important confounders. I don't need to convince you that age, CHATS, BASC score, CHATS and mobility index, history of AFib, CKD, or hypertension are, of course, confounders in this association, and therefore we do have quite substantial evidence of residual confounding here, only looking at observed confounders. Now, if we then look at, next slide please, if we then look at the negative control outcomes, in this plot that I will show you a few times, what you have here is the true hazard ratio expected to be 1, that's denoted by the line in the middle. And then you have in the y-axis the standard error, and the red dashed line show basically the line for significant association. So anything within the funnel, within the kind of inner part of the dashed lines, would be not associated with the exposure. Anything out of those lines would be associated with the exposure. In this particular example that I'm covering, we had just over 20% of the negative control outcomes associated with vaccination status in both cases. So we deemed this to be evidence of unresolved confounding, and we did not go ahead with the analysis of vaccinated versus unvaccinated in this instance. Next slide, please. Excuse me. Now, if we go for objective 2, which a priori one good thing would be easier to compare using an active comparator arm, what you see here now is a similar plot to the previous one, comparing 1 dose Vaxzevria versus 1 dose Comirnaty in CPID Aurum, and you can see how before matching there was strong evidence of differences between the groups, with lots of dots crossing the 0.1 line in the x-axis. But after propensity score matching, you don't see any single dot above the line of 0.1. So you have evidence that by using propensity score matching, you have substantially reduced observed confounding. Next slide, please. If you then look in this same example at the negative control outcomes distribution, in here there was only 1 negative control outcome that was associated before calibration with vaccine brands. Of course, 2% could be pure chance, and by applying calibration, we basically corrected that, and we have no negative control outcomes associated with the vaccine brand used. But of course, we had a threshold of less than 20%, so 2% is really already a good result even before calibration. Next slide. Another example here of comparative risk, now comparing Janssen 1 dose versus first dose Pfizer BNT in an American open claims data set. Again, good evidence that we managed to reduce observed confounding quite substantially here. As you can see, looking at the x-axis, loads of, well, not loads, but a few dots showing an imbalance before matching, but then the y-axis shows no dot 1, so demonstrating the value of propensity score matching as expected. Next slide, please. If you then look at negative control outcomes, I think this is a beautiful example where to the right-hand side of the dashed line, you see loads of dots. This is 28% of the negative control outcomes fitted were associated with vaccine brand in this case. And in here, you see actually that most of those dots are to the right-hand side, meaning that these people, despite propensity score matching, are more likely to accrue comorbidities, to have other outcomes that are not associated with vaccination. So this is, I think, a beautiful example where calibration, now on the top part of the plot, basically corrects for that and calibrates the estimate, and then you get only 5% of the negative control outcomes associated with vaccine brands. Next slide, please. Okay, just to finish with the final results of the study that was published in the VMJ, as you can see, picture there is Shinton Lee, who is one of my brilliant PhD students who led on these analytics. Next slide, please. I'll go through these relatively quickly. Basically, this is the report of the comparative risk of thrombosis thrombocytopenia associated with adenovirus versus mRNA-based COVID vaccines, using data from Germany, Spain, France, Netherlands, UK, and the USA. Methods I've already covered, and we did meta-analysis across databases where there was sufficient homogeneity. Next slide, please. Again, this is very much in line with what Katia was reporting earlier on the data assets available to us. Next slide, please. Just a flowchart to see how propensity score matching got rid of loads of uses of vaccine, but resulted in comparable groups of people receiving the Charos 1 dose or the BNT 1 dose vaccine. Next slide, please. And this is the most meaty part of the illustration of these negative control outcomes, where you can see how in the top part of the figure for thrombocytopenia, we did see an observed increased risk with Charos 1 dose compared to BNT 1 dose. The calibration, which is here shown as a slightly thinner kind of confidence interval and a white dot instead of a purple dot, didn't really make much of a difference. It moved the result a little bit to the left, so closer to the null, but it didn't really make a difference. For thrombosis with thrombocytopenia, which you see in orange at the bottom of the plots, and this is now comparing Janssen with BNT 1 dose, you do see how calibration moved the estimate from statistical significance to borderline significance, which, you know, for people who believe in statistical significance as a kind of matter of faith, would be a deal breaker. For me, it just corrects the estimate, but it is, you know, there's still, I would say, evidence of a potential association there. Next slide, please. I just want to finish by saying that when using negative control outcomes for empirical calibration, and I think this is very much in line with the comment from Xabier earlier, you have a kind of trade-off between type 1 and type 2 errors. There's 2 papers we published in Frontiers in Pharmacology last year looking at different methods for vaccine safety using previous vaccines like flu, HPV, and so on, using American data, where you can see how in blue those bars denote very high type 1 error when using historical comparisons or observed versus expected analytics without calibration. However, when you calibrate, you take that basically to the null, but you increase your type 2 error. Not as much as type 1 error was, so you know, you are correct in that, but there's still a risk that by decreasing dramatically your type 1 error, you're incurring some type 2 error, and that's something that we should bear in mind. And I will finish with my last slide, if I still have time, just to say, these are my own conclusions, of course, to be challenged with the discussion. Negative control outcomes are useful as diagnostics as well as mitigation measures for residual confounding. We use them successfully in COVID vaccine safety research, and kind of negatives are they require large sample sizes, thorough work on selection and validation, and as I said, empirical calibration will lead to a kind of trade-off between types of error that you're happy to commit to. And I will finish there, and we'll be very happy to take questions or to stay for the discussion later. Thank you so much, Miriam and team.
Thank you, Dani. Thank you very much, Dani. Is there any question? Yes, Olaf.
Thanks. Thanks, Dani, for a very nice presentation. Just on the very practical question on the 20% cutoff that you mentioned for either proceeding with the study or go for the calibration. Is there any rationale for that? And should you also consider that in sensitivity analysis and maybe take different cutoffs? Because if you let's say stop when there's more than 20% of association with negative control outcomes, you might also lose a lot of information that is useful for decision making.
Yes, very fair. Olaf. So I don't think there is any valid threshold, to be honest. There is, of course, the kind of chance threshold that you could say, less than X% is chance, right? But there isn't really a valid threshold. We did go for 20% based on previous experience, but we could have done sensitivity analysis, as you say. I think what is important really is that if you use it as a stop-go criterion, you could specify that, of course. So regardless of whatever threshold you go for, this has to be agreed, in this case, with the funders of the study and with your colleagues and pre-specified, and then you have to follow whatever you pre-specified, right? It is very tempting to say, oh no, I'll just change it to 25% because the data is that has 24% error. So I think the specification is the key here, but I don't think there is solid evidence that there is one threshold that we should use.
Thanks. Thank you.
Okay, thank you. There are no more questions, but Dani, I have one for you, which is like the 93 negative control outcomes. I understand these are like vaccine independent, correct? So they have been assessed for all type of vaccines. Do you think that is useful? Because there may be different, relationships with the vaccines. And could you explore a bit more, or explain more what type of conditions are on this negative control outcome list?
Well, you got me there. I think I remember the list. And I can tell you that I don't know what we evaluate this long list for any vaccine. There are some of them that are, I think, better at sharing compounding structures with vaccines that we use in more frail people, like, seasonal flu, COVID vaccines, and so on, that we thought would work best for COVID-19 research, whilst others, like the ones that we think share more of a confounding structure with HPV vaccination, of course, do not really apply to COVID, right? So that's why we had that intermediate step where we had some clinicians basically going through the list and validating. If I remember correctly, most of the things that we had to do with things like, falls, fractures, ear infections. So no surprise that I think most of the things we had more of, have been used by other groups as well. Some other things might look maybe more exotic in that they probably are more relevant for, things like HPV vaccination, right? There is a group of thinking, I would say, there's some people who believe that sharing of confounding structures is less important if you're using more negative control outcomes. I think I sit on the fence a little bit on that one, and I don't have a very strong opinion on one or the other. But I think we made sure that we had some solid negative control outcomes that really shared structures with COVID vaccination rollout during 2021. But others that I would agree are probably not that relevant for COVID and are probably better for other types of vaccine.
Thank you, Dani. I think, yes, we have a question from Saad.
Thank you. Thank you very much. The question is to you and to the previous speakers. The negative controls with COVID, initially there was huge numbers, but very quickly they were reduced because the negative controls got vaccinated. And we ended up with a much smaller number. And the characteristics of the negative controls at the beginning, say in January, February 2021, were different from the negative controls in April, May. They were people who didn't get the vaccines for a reason other than the healthy non-vaxxers and anti-vaxxers. So at what stage, did you take into the account where you would examine the comparison with the negative controls in COVID vaccinations? February, March, April, May?
So all our analyses were stratified by periods, if I remember correctly, by month. I don't recall any impacts on negative control outcomes, but by doing that, you sacrifice a lot of power. So I'm not 100% sure that we don't have any evidence of that. It's just that we probably have smaller numbers. So you're not convinced that we have an answer for you, unfortunately. So.
Okay, thank you. Then thank you, Dani, again, and also no pepper nuts for you. But once you come to the Netherlands, we have a load in Rotterdam. Good. So we move on, and I would like to invite Rosa Gini, who is Director of Pharmacoepidemiology at the Agenzia Regionale di Toscana, and she will talk about use of negative controls, concepts, and caveats.
Thank you, Miriam. Okay, my slides are on time, huh? And also I can press the button. That's good for me. Okay, so thank you very much. So when Miriam and Olaf asked me to prepare this presentation, this is a topic that I am interested in. I've been interested in for a while, but I went to the NCEP methodological guide to see if there was anything new, and there was a lot, actually. There is this 5-hour public workshop, which is available online, and I definitely recommend all of you who are interested in this topic. It was held in March, so it's very updated. So what I decided to do is to go through my 5 hours and try to pick up some interesting things for you. But please, I really invite you to go through it. And it was organized by the FDA. Actually, so it was a joint initiative by the Duke Center for Health Policy and the FDA. So, starting point, and I think that's something that Sophie was saying as well. What are the risks for FDA? And I'm really just showing you some slides I selected some slides and I will try to comment them. So, threats to the validity of observational studies. Well, random, we don't care. Systematic is, remember that, selection bias. Okay, confounding, which is considered what we address more often. But then information bias, misclassification. Okay, so these are the 3 enemies. And unmeasured confounding is somehow the thing that in this discussion that was held here, with some exception, was considered to be what is addressed by negative controls, even though. So so we said concepts, right? Basic concepts. Negative controls can be either negative control outcomes that we have seen earlier also today, or negative control exposures. So I will put myself here. So what are the assumptions? The assumptions are that there is no causal, these arrows don't exist, right? But then there is also the assumptions that measured and unmeasured confounder structure is the same, right? Both for negative control exposure and for negative control outcome, which is a pretty strong assumption, right? But if this happens, and we have seen earlier examples where there are attempts to make this happening, then a lot of positive things can follow. Why? So the method in itself, and I really invite you to read this because it goes unnoticed sometimes, it has the potential to address unmeasured confounding as well as information bias and selection bias. So I think, and it can be used to detect bias. It can be used to detect all of those biases. And more tempting sometimes, it can be used to reduce or correct bias. And sometimes what I think is that in order to obtain this very tempting result, to really eliminate the bias, due to a measuring confounding, you are throwing away the opportunity to detect bias for the other causes, okay? And this is somehow the line that you will hear in this presentation, because negative controls are a great opportunity, so let's not spoil it. And indeed, FDA considered this a great opportunity, an emerging field, methodological field, so that in its next 5 years, program, it has started a program on negative controls. This workshop that we saw is part of that, and then there will be 2 methods development projects by September 2024. So in March, they were already programming the project next year. One, to develop empirical method to automate the negative control identification, which is a problem that we have seen already. And second, develop a method to use double negative control adjustment, and I will try to tell you something about this, to reduce unmeasured confounding. This is our only enemy now. And all of this to include everything, integrate things in the Sentinel system, which is the FDA somehow real-world evidence box, let's say. So these next slides are adapted from a document that you can find in the website of the workshop, where Professor Shi just listed a lot of techniques for negative control adjustment or assessment, with their description, key assumptions, strength, and limitations. Okay? I will go through all of them, but just stop through some of them. So the first 2 are just separately bias detection or adjustment, either via NCE or via NCO, right? So consider the 2 possibilities separately. The thing is, and there is you have all the references if you wish, that if all of those assumptions are met, so if you have an exact same structure, a theorem states that you can adjust. You just need one, okay? You just need one negative control exposure or one negative control outcome, and magically, as a consequence of your very, very strong assumption, there is a theorem that proves that, and some other assumptions that you can, there are some assumptions on linearity, and of course this is also the limitation, that you are making very, very strong assumptions. But if you have that, it works. Okay, so that was like 12 years ago, I think, this was starting to be developed. And then this became, it's all the same group that went through in the past 10 years and evolved in this technique, this COCA, control outcome calibration, and then DID, so differing differences. And you can have a look and see what the details of those techniques are. And we finally land into this double negative control plus dance. So what is that? Again, double negative control method and the data-driven automatic negative control estimation. DANCE is the name of the algorithm. So what is that? Now, this is the case where we have a pair. You have both a negative control exposure and a negative control outcome. And all of those assumptions are satisfied. This is the idea of the double negative control definition. And if you have that, then you have a very simple linear, very simple, some linear assumptions, and you can estimate the average treatment effect in the population. Use this simple formula. And if you want to try some fancier association, so some fancier models, you can also do that, because the application is straightforward. And what is the intuition is basically that using one of those elements, so one of those associations recovers the confounding bias up to a scale, and using the other, you can recover the scale. It's of course sophisticated, but it's not dramatically sophisticated. You go through it and it makes sense. What is the next step? So, double negative, let's restrict to the case where our double negative are also not really associated with, so the negative exposure is not associated with the treatment, and the negative outcome is not associated with the outcome. That's a special case, right? So we are putting ourselves in a smaller box. Why that? So we would find less such pairs. Why do we restrict to that? Because, so these are called, how is that called? Disconnected negative controls. Why do we like them? Because the existence of those two outcomes can be tested statistically. Because if this is the causal situation, you will have a rank deficient matrix here, and you can put up a statistical test to make sure that this happens. So basically, the dance algorithm, it's a kind of automatic search for such pairs. Actually, you need to look for triplets for technical reason that you would find, and thanks to that, you could generate an ample, if there is any, because there is no guarantee that such triples exist, but if they exist, you can find them automatically. So that's the idea. So the funding from the FDA is to set up all of this system and see if it works, and then if it works, what happens, right? And it is 1 year of study, and then they have other work to do. Okay, so concepts, caveats. What I don't see in this thing is the misclassification. And if you think of health-seeking behavior, you will see health-seeking behavior is something that induces differential misclassification. Why? Because if you have your exposed people, there are people that they vaccinate, right? So if they have otitis, they will go to the doctor, while these other people, maybe they will go less to the doctor, and actually the risk is the same across both, but you just see them more. So this is differential misclassification. That's something that we have in our data, and the negative control helps you identify that, because they do realize that there is such problem. And I don't understand in the framework that we have seen earlier whether this is taken into account. So if you see this star, this is the common notation for the measurement of your outcome, and I don't see that in this framework. So that's my curiosity, and I would like to go further into that. And then the last technique is the one that we have seen earlier described by Dani. And so I will not describe it more, and probably more of you are familiar with it. But it has the problem that Xabier and Dani and his group, because this study by Nicolas is actually co-signed by one of the authors of the methodology. The problem is, of course, that you kick off false positive, but you also just eliminate true positives, and that's, of course, a problem. And in the panel, in the workshop, that was, of course, raised as a concern exactly for the same reason as Xabier did. But I have an additional problem with this methodology, which is actually the way synthetic positive control are generated in this case. So let us be again in the case where we have our risk of our negative control measured into our database. But it's a measurement, right? And I assume that there is no non-differential misclassification. It's okay, it's a negative control. So, but we do know that there are more cases there, right? We don't see them, but they are there. And normally our outcomes are less sensitive, so they have more false negatives than false positives. So this is the regular situation. And how do they create the synthetic positive control? They do this. So they take in the non-exposed the same people as earlier, and in the exposed they take the same people as earlier, and then they double them. And they claim that this is a synthetic positive control with a relative risk of 2. However, well, we still have those that we didn't see earlier. So it's actually, you are not actually doubling the risk, you are just increasing it a bit. And they are aware of that. And for this reason, they add the assumption that the synthetic outcome has the same measurement error as the observed outcome, so that there is these additional events that we don't know how many they are, we don't know who have them, and they make the assumption that this gray thing exists, which is not even an assumption that you can challenge, because it is, I don't know how you can make it. Okay, so before wrapping up, I made the wrong order of slides. There is this paper that I also invite you to look out if you wish. So this is the consequences of violation of assumptions of all the methods that we saw earlier, except the last one, because, yeah, even violations. And to wrap up, potential of utilization of negative controls are wide, and they are definitely something promising that we should look up for, and it's a methodological advance that we want to see how it goes. It must be very nice, and there is this thing that FDA is doing where, well, we will definitely we'll see what happens, and then there are some violation of assumption or some weird assumptions that we should look for, because, of course, this is always the risk when we do sophisticated methods.
Thank you. Thank you very much, Rosa. One question, we are running out of time, so we will have some discussion. I guess we're going to move the coffee break a bit, and maybe, Olaf, can you shorten your wrap-up? Yeah, okay, good. Okay, good. All right. So I have gained some time here. Thank you, Rosa, very much. So let's move to the last presentation in this session before we go to a panel discussion. And so I think we have heard now a lot about the use of negative control outcomes and positive negative exposures. I think it's an area of exploration, so we will talk later how that can be utilized. But before we go to the panel discussion, we are also going to talk about another methodological issue which is really important, and that we often estimate multiple dose effects. And there is this whole causal framework, actually, and Xabier, Garcia de Albeniz Martinez, who is the Director of Epidemiology at RTI Health Solutions, is going to explain to us on how we can emulate the target trial to study multiple doses of COVID-19 vaccine safety. Thank you, Xabier.
Thank you. Thank you, Miriam. Thank you, everyone, for being with me now. That we are out of time and we are all tired. I'll try to make this entertaining. Okay, so I'm going to talk about how to study the effect of different dosing of COVID vaccines. So first I want to apologize because I'm going to explain things in a very simplistic way. So if anyone feels insulted for the simplicity of the slides, I apologize. So this talk is going to have two parts. The first part is going to be a thought experiment. We're just going to come up with a complex design and see which are the challenges and how can we address those. And the second part will be an application. But it won't be an application in the form of an analysis of a database, because I'm not there yet, I'm sorry. It will be an application in the form of how we use this framework to guide a discussion with clients when they ask for things that might not be correct or might have biases and they don't see it and you have to make them see it. So that's going to be my application here. So when we discuss methods or design with clients, the first thing we try to do is putting everyone in the same page. And we try to do that by outlining which are the assumptions that we use in pharmacoepidemiology. And we try to do that by using the different names that people give to these assumptions, because Sometimes you are lucky and you discuss your design only with epidemiologists, but other times you have to discuss your design with clinicians, statisticians, people who don't have any connections with healthcare. And we all work with the same concepts, we just give them different names. So the two basic assumptions that we work with when we do pharmacoepi is first, non-measure confounding, which means that we are doing a fair comparison. We are comparing apples to apples. That's why in randomized clinical trials we randomize, because we want to make sure that the only difference between our two groups is the exposure. All the rest is exactly the same. That's the first assumption. And as I say, people call it in different ways: exchangeability, non-measure confounding, comparing apples to apples, etc. And the second assumption is that once you are evaluating people for the occurrence of the outcome, you are not allowed to cherry pick who do you want to analyze. This is why trialist says once randomized, always analyzed. In pharmacoepi, we call it in many different ways. We call it selection bias, immortal time bias, prevalent user bias, healthy user bias. It's just selection. Okay, so let's go for the first part, the thought experiment. I have to discuss how to study different doses of vaccines, and I just came up with 4 different questions. I'm going to read them. So, one example could be, what is the effect on the risk of death? I just chose this outcome. Of receiving a full vaccination schedule consisting of 2 doses compared with no vaccination. Another example could be the same, but instead of studying 2 doses, we are studying 3 doses. 2 doses for the primary vaccination plus a booster 8 months afterwards compared with no vaccination. Then a third example could be, what is the risk of death of receiving at least 1 dose compared with no vaccination? And a fourth example could be, what is the effect on the risk of death of receiving a booster of the COVID vaccine compared with not receiving a booster? So why am I giving you 4 examples? Because they can be classified in 2 main groups, and these 2 main groups will have different methodological implications. The first 2 examples study exposures that are sustained over time. When you receive 2 doses of the vaccine, you have to be alive to receive the second dose of the vaccine. And you need to have had no contraindications. So if you have an anaphylaxis after the first dose, probably they won't give you a second one, right? As opposed to single-time exposure, which is something that is very well defined at baseline. You don't have to look into the future to see whether your individuals are in one category or in the other. So let's choose the most complex example, which is this one, to do our thought experiment. This research question is, what is the effect on the risk of death of receiving no vaccine, 1 dose, 2 doses, or 2 doses plus a booster? So if we want to answer that question, we can just design a randomized clinical trial where we select a bunch of eligible individuals and randomize them to the 4 arms. 1 arm is no vaccination, and then another arm is single dose, 2 doses, or 2 doses and a booster. And you're probably thinking, why is this guy talking about randomized clinical trials if no one here does randomized clinical? That's not our business, right? Well, because that's a way to guide the discussion. Because most of the people, clinicians, trialists, other people involved in research, are more comfortable discussing a randomized clinical trial where you are isolated into an optimal research environment where you have control over exposure, as opposed to discussing an observational study where you have to discuss many other aspects like censoring, follow-up, etc., right? So that's why the target trial emulation framework exists. This framework, I'm sure you've heard of it, and tomorrow we will talk more about this, stems on the fact that for every causal question, we should be able to come up with a hypothetical target trial. If you have a causal question and you don't know what is the trial that would answer that question, you might need to rethink that question because maybe it's not causal. So emulating a target trial is very simple. You just come up with your hypothetical trial, which is what we saw in the prior slide, and then try to emulate each of those components, each of the components of that target trial. One of the main aspects, the main benefits of emulating a target trial is how you treat time zero. Time zero in a real trial is the time when you apply eligibility, randomize people, so you assign treatment, and that's the time when you start the follow-up. When those three elements are not aligned, then you might have selection bias. But if they are aligned, you won't have selection bias, most of the cases. But sometimes aligning those is not easy. So let's see how we do it in this thought experiment. So to solve this design, the first thing we do is creating this table, which if you have read target trial emulation papers, this type of table is in every paper. And in this table, you have in each row each of the components of your target trial. You have eligibility criteria, vaccination strategies, treatment assignment, outcomes, follow-up, causal contrast, and statistical analysis. And in this column, you just dream, you just write what's your hypothetical target trial, and then the column on the right, you have to write how you're going to emulate each component. Some components are very easy to emulate, for example, eligibility criteria or vaccination strategies, you just use the same. Other components will be more difficult. So in our case, we have our 4 vaccination strategies, which are no vaccination, single dose vaccination at baseline, first dose at baseline, and a second dose within 3 to 6 weeks, of course, only in the absence of a contraindication. If you receive a first dose and have an anaphylaxis, nobody is going to give you a second dose. And the fourth strategy is receiving 1 first dose at baseline, second dose within 3 to 6 weeks, and a booster 8 months after baseline. Okay, so to emulate this trial, we have 4 problems. The first problem is that there will be multiple eligible times. For those who receive a vaccine, in my observational data set, we are now into the emulation phase. We already specify our target trial, now we have to emulate it. So, those who receive a vaccine, the time zero is very clear for them. It's the time when they receive the first vaccine. But those who do not receive a vaccine, when is their time zero? I need to define that at baseline. And in my study period, if my study period is 8 years, 2 years, and someone didn't receive a vaccine during those 2 years, which day of those 2 years is the time zero for that person? Here I have 2 options. I can choose a single time zero for that person, random one, or the first eligible one, or I can choose every eligible time, and that's a more efficient approach. How do you do that? One way to do that is what we have seen in many of the studies of COVID vaccines, where they divide the study period in weeks, for example, and each week they evaluate eligibility, and for those who are eligible, those who didn't receive a vaccine, that week go to the no vaccination group, those who receive the first dose go to the other strategies. And you do that for every week of your study period. Here is more important evaluating eligibility at the beginning of each week. Someone who's eligible here might not be eligible here, and also extracting baseline variables at the beginning of each week. Second problem, some of our vaccination strategies are not defined at baseline. For example, what happens if a person dies 2 weeks after receiving a first dose? That person is compliant with 3 strategies. She's compliant with the single dose strategy because she received the first dose. She's also compliant with the 2 doses strategy because she received the first dose and died here. And the same for the 3 doses strategy. So, where can I classify that person? Again, here I have 2 options. I can clone that person, create a copy in my database and assign one copy to each arm. Or I can say, okay, I don't know which strategy I should assign you to. I will just pick one at random. Okay, so this is more or less how our target trial emulation will look like. We will have a bunch of eligible individuals. Some of these don't receive vaccination at baseline, so they go to the no vaccination group. And some of them receive a vaccination at baseline. And here I create three copies. One copy goes to the single dose arm, another to the 2 doses arm, and another to the 3 doses arm. Then to evaluate the effect of each of these strategies, I need to censor these individuals when they stop following the assigned strategy. So for example, somebody who is assigned to the single dose arm, if that person receives a second dose, that's the time when I censor that person. Somebody who's assigned to this 2 doses arm and she fails to receive the second dose in the time period that I want them to receive it, again, I will censor them at the end of the grace period for the second dose, and so on. Third problem, the same problem that we have in every observational study, baseline confounding. People who get the vaccine might be different that don't receive the vaccine, so this is business as usual. I need to characterize appropriately people at baseline, and we just had a talk about negative control outcomes. I don't need to explain this more. Fourth problem, post-baseline confounding. This is why I wanted to make the difference between strategies who are well-defined at baseline versus strategies who need intervention sustained over time. When I applied the artificial censoring that we saw before to select the person time who is compliant with each of those strategies, I might be introducing a selection bias. Because people who adhere to a specific treatment strategy might be different from those who do not. And that adherence might not depend on a baseline variables, might depend on variables that happens after baseline. And to make things more complicated, those variables, those post-baseline variables might be influenced by prior treatment. So you need specific methods to deal with that. You have to make one assumption that is very similar to the assumption that we use to adjust for baseline confounder, which is that we appropriately measure all the confounders. So here you have to assume that you appropriately measure all the baseline and post-baseline confounders, and then use appropriate methods like inverse probability weighting to adjust for that. Okay, so this is the summary of the 4 problems that we have to face when we design a complex study like this one that attempts to evaluate different duration of treatment, different doses of vaccines versus no vaccination, multiple eligibility, patients' data being compliant with more than one strategy at baseline, baseline confounding, and post-baseline confounding. This was the thought experiment to show these challenges and potential solutions. Now let's go to the application. As I mentioned before, the application is a discussion that we had to have with a specific client. This client asked us to estimate the effect of those 2, of vaccine A versus those 2 of vaccine B. I didn't know what they meant by those 2. So I just came up with the simplest scenario. A scenario, you have to make your life easy when you can. So, hey, that's making your life too easy. It's not fair. Thank you. It's only 4 minutes and I'll be done. Okay, back to where I was. So they wanted to study the effect of those 2, of vaccine A versus those 2 of vaccine B. So I came up with this. Let's compare the second dose of vaccine A versus the second dose of vaccine B. That is a single-time exposure. You just study people who have an indication for a second dose, right? And classify them into A or B according to whether receive A or B. Easy peasy. You only have to adjust for baseline confounding. But they didn't want this. They wanted time zero at the first dose. So then we told them, okay, what you want to do is estimating the effect of receiving 2 doses. That's a strategy that is sustained over time. That complicates things because time zero must be the first dose, and then you have to do what we explained before. You have to censor people if they deviate from the assigned strategy, and then use some methods to adjust for the potential of selection bias there. So we even came up with very simple diagrams like this one. This is the data that we could have in our database. In our database, we will have patients who actually receive 2 doses of vaccine A in the time that they are expected to receive it. There will also be patients who receive vaccine A too late, patients who didn't receive a second dose at all, and patients who mixed brands, right? If this is what we have in our database to estimate the effect of 2 doses, we have to do this. We have to select the compliant person time. So, for the first example, all the person time is compliant because they received the second dose when they were expected to receive it. The second example, they stopped being compliant when they didn't receive the vaccine by the end of the period that they were supposed to receive it. The same with the third case, because they didn't receive any second dose. And in the fourth case, they deviate from the assigned strategy when they receive a different brand. This censoring means that after this, you don't observe outcomes. But before this, you do observe outcomes, right? As opposed to what they wanted to do. They wanted to just analyze people who received 2 doses. All the rest out of the analysis, right? What happens here? That if you have an adverse event here, you're probably more likely to not receive a second dose. Or you're probably more likely to change brands. So by excluding these, you are effectively getting rid of a number of ARSs in your database. So this is selection. This is selection bias. This is a fancy picture, but if you want a causal model, this is the causal model, where you have your exposure is a time-varying exposure, where you have dose 1, dose 2. An ASC can be affected by the first dose. An ASC can affect whether you receive the second dose or not. You are conditioning on the second dose to analyze your data. That's conditioning on a descendant of a collider that introduces selection bias. Tomorrow in the target trial emulation course, we will talk a little more about DAX, although I think, based on the prior presentations, I think everyone is very familiar with this. But anyways, okay, so this is just the summary. Studying different doses of the vaccines might imply studying vaccination strategies that are sustained over time. And you have to be careful to how you select the person time to analyze that, and you cannot just exclude people from your analysis based on post-baseline events. That's pretty much the summary of everything. And if you like target trial emulation, we are doing a course in Barcelona next March. This is self-promotion. I'm sorry, Miriam, I didn't warn you about here. This is happening in March. Spring is beautiful in March, so please come to this meeting. Exactly. Thank you.
Well, thank you very much, Xabier, and the self-promotion is really nice, actually. So, any question? I think this is, the second dose issues. I mean, I think you explained it very carefully and nicely that how we should do that. Comments, questions? Otherwise, yes, Oshin.
Oh, Tom, great. Thanks, really nice. So I was wondering about whether there are trade-offs on computational feasibility when you take this sequentially emulated target trial approach. So as I understand it, to correct for this fact that people are in multiple arms. People often use things like bootstrap analysis. And if you're dealing with very, very large administrative data sets, you're now copying cases several times, so you blow up the size of the data set, and then you have to bootstrap from that, which we had a discussion yesterday morning about how upsetting that is in practice. But do you see this as like a practical constraint, or do you think there's a way around this?
It's a problem, because when we clone, we introduce autocorrelation, so the traditional estimators of the variance are not useful anymore. So you have to bootstrap, and as you mentioned, bootstrapping means repeating your study 500 times, the whole study 500 times, and that might not be feasible. There could be workarounds there. For example, and this is something that we are working in ROC20 with Svetlana, which is there. You can try to identify the most computationally expensive step on your analysis and try to substitute that by something that is less computationally expensive, and see how much time you gain there. We're doing that with Svetlana by substituting matching, time-specific matching with a random assignment of time 0 and then adjusted by calendar time. But you are very right. Sometimes this complexity bring in computational burdens that are very serious. That's correct.
Thank you. Thank you very much. And let me not forget the peppernuts. Thank you. Rosa, I forgot you. Okay, so